So good afternoon and welcome to the weekly Urban Water Innovation Systems Research Webinar Series. We're delighted you could join us today and look forward to your continued participation on our ongoing webinars. Our first series, Thrust A, is focused on enhancing our fundamental understanding and characterization of the sustainability of urban water systems by comparing trends in the past with alternative future land and water use, population, and climate scenarios. The seminars included in this series are organized by three themes. Theme A1 characterizes water supply and demand patterns under future socioeconomic scenarios. Land and water use, land cover, and socioeconomic scenarios are used to assess two-way interactions and feedback between urban form and land atmospheric processes. Theme A2 assesses the impacts of urban water systems on urban heat islands and the regional climate and the ensuing co-benefits for human health. And finally, theme A3 examines effects of change in climate, population, demographics, and policy on hydrologic and ecologic processes over the observed past and future assessment periods. Our weekly webinars will meet most Thursdays at 4 p.m. Eastern Time. This is a schedule for all of the upcoming presentations for the Thrust A webinar series. Please note that there is no webinar scheduled for May 4th. This schedule is also available on the UN website under the Education tab. A couple quick housekeeping items before we get started. All participants are entered muted, but I will be tracking your questions throughout the session, and we'll answer and address all of those at the end of Tom's presentation. You can use the questions queue or the chat queue to ask any questions, and we'll get to those at the end. These sessions are all going to be recorded and they'll be available on our YouTube channel. The links will be distributed to the entire UN network within a couple days after the presentation. There is a follow-up survey that's going to be sent out after the final webinar in our series on June 15th. Please take a moment to answer the 5 short questions and provide some meaningful feedback so we can continue to improve and create engaging and meaningful webinars. So without further ado, I am pleased to introduce Dr. Thomas C. Brown, Research Economist at the U.S. Forest Service Rocky Mountain Research Station in Fort Collins, Colorado. A member of the station's research staff since 1974, Tom has focused on methodology for economic valuation of natural resources and the environmental, economic, and institutional aspects of water resource management. His recent work includes an assessment of past and projected future water use in the United States and the book In-Stream Flow Protection, Seeking a Balance in Western Water Use on the law, policy, history, and economics of water management in the Western United States. He has published widely on water resource issues and the valuation of ecosystem services. Tom received his bachelor's degree in economics from American University and his master's and PhD in water management and economics from the University of Arizona. And with that, I'm going to turn the controls over to Tom. Bear with us for just one moment throughout this transition.
Okay, thank you, Sarah. So hello, everyone. I'll be describing a large new study I've done with Jorge Ramirez at Colorado State University, along with a postdoc for a while with us, Vinod Mahat. This study is a newer version of an earlier study that Jorge and I and others finished 2 or 3 years ago. This new version uses newer climate data, uses a different water yield model, more recent water use data. It models water supply and demand at a finer spatial scale for smaller watersheds, or I'll call them basins, than we used before. And we use a different water routing model. And so here we go. The goals of this study were to determine how water supply vulnerability across the conterminous U.S. is likely to change over the remainder of the century, assuming no new efforts to adapt to changing circumstances. And then secondly, to explore the effectiveness of some basic adaptation options. You might ask, why do a nationwide study like this, since studying it over such vast scales doesn't allow the sort of fine-tuning you would need to do to really understand the situation in a given basin, to understand it well enough to actually make some decisions about, say, a certain adaptation possibility. And the value of this large-scale study that we see is that it can account for the interconnections among multiple and often quite distant basins, and it can achieve a methodologically consistent estimate across all basins of the relative water supply vulnerability and of the relative effectiveness of some basic generic adaptation options. So, also by way of introduction, I guess we define vulnerability for this study as the frequency of water shortage. And I'll go into some detail about goal 1 in this presentation, and then goal 2 will be addressed pretty quickly at the end. For goal 1, we estimate the frequency of future water shortages in basins throughout the U.S. under future socioeconomic and alternative climatic conditions, assuming, first of all, that only renewable water is available for use. So no groundwater mining is permitted. Groundwater withdrawal pumping is, but only of recent recharge. Secondly, we impose an in-stream flow constraint of 10% of past flows, average past flows. Third, we extend past trends in water use efficiency, for example, and other factors affecting water use like irrigated area and in electricity use, etc. And then we allow no major new adaptations to impending shortages. So we hold reservoir storage constant at its current level. We hold also transbasin diversion capacities constant at current levels. And then, as stated earlier, for goal 2, once we establish what would happen if no efforts were made to address the shortages that show up, we see what such adaptation options like allowing groundwater mining or enlarging reservoirs, what that does to the projections of future shortages. We're doing this modeling of water supply and demand at the HUC4 spatial scale. So there's 204 HUC4 basins in across the 48 states, and we're modeling at a monthly time step. And a shortage occurs when demand in a basin exceeds available supply. And we measure shortage frequency for each of several 25-year periods. So we count the number of months during a 25-year period when shortage occurs, and that's put over 300, which is the number of months in a 25-year period. And we get a proportion of months or a frequency of shortage for each basin. So there are 5 basic steps under goal 1. And the first basic step is to obtain projections of drivers of water supply and demand. And these basically are the climatic drivers and socioeconomic drivers. The climatic drivers are for 2 RCPs, the RCP forcing level 4.5 and 8.5. And you can see a picture here of the emission levels and CO2 concentrations for those RCPs over the century. I won't go into the details because I'm assuming that everybody knows about these RCPs since they were used in in the 5th IPCC assessment. And we use these 7, or we use projections from these 7 GCMs. And we obtained those projections in downscaled fashion from the U.S. Bureau of Reclamation's website. These are all CMIP-5 climate runs. So we have, therefore, 14 different futures. These 7 models were used with each of the 2 RCPs. And here are some graphs of mean temperatures and precipitation levels, across the U.S. for 5 20-year periods. And you can see on the left that temperature on average is increasing over time, as certainly expected. The darker lines there are the RCP averages. You can see that temperatures with RCP 8.5 tend to be higher than those for 4.5. You also see that there's quite a variation among the 14 futures. The GCMs are projecting different temperature levels over time, although pretty much always increasing. On the right, you see precipitation, and this is a different picture. The RCP averages are practically on top of each other, but there's a great variety or variation among the different futures. With precipitation actually decreasing a little bit in the near future, and then largely increasing on average, although decreasing with some futures and increasing quite a bit with others. So there's a lot of variation in the precipitation projections, and therefore a lot of uncertainty about what's going to happen. Here's a picture of the temperature changes, 2 maps for the 2 RCPs. And as shown before, temperatures are increasing more with RCP 8.5, and this map shows that they're increasing almost everywhere more with 8.5 than 4.5. Here's a picture of the change in precipitation. It's a complex situation, really. The blues show increases from the recent past to the 2080 period, a 20-year period centered at 2080. So mean precip levels, or the change in mean precip levels. The reds show decreases over this long time span. And the greatest decreases are in parts of California and the southern Great Plains and parts of the Southwest. The decreases are larger for 8.5 than 4.5, but so are the increases in other parts of the country, larger with 8.5 than 4.5. So the other set of drivers, socioeconomic drivers, I won't say much about them. I'll just show this one chart of U.S. total population from 1960 on to the end of this century. The past population growth has been quite regular. We've been adding in this country about the same number of people each decade. And the projections, which largely come from the Census Bureau, but have been extended on by us, based partly on work by the IPCC, or revealed in that assessment, you see that the trend is downturning a little bit in the second half of the century, but by and large a consistently increasing U.S. population in total. Basically, it's assumed that immigration will continue over time. So there are, or let me say that step 2 involves estimating water yield given the climate projections for those 14 futures. We used the Vic model this time to estimate water yield. Here's a picture of mean annual past water yield across the U.S. From the Vic model runs. It was run for each more or less 12 square kilometer cell across the country. And as is well known, water yield in the western half of the country tends to be concentrated in the Pacific Northwest along the Cascades and the coast, and in the high elevation portions of the Rockies. Here are 2 maps of the projected percent change in yield from the recent past to the 2080 period. These maps look something like the change in precipitation, but the areas of decreasing yield are much larger than the areas of decreasing precipitation, and that's obviously because of the increasing temperature. So, for instance, we have in the upper Midwest and in the South, where precipitation was shown to increase, we have yield projected to decrease in a lot of places because of the rising temperatures using more of the precipitation as through evapotranspiration. So step 3 was to estimate water demand given future population and income and other socioeconomic conditions, and given the climate. I won't say much about the water demand projections. There's a lot of detail behind it. I'll just summarize it briefly. Here's a graph of past and future water consumption in the U.S. by water use sector. As is well known, agriculture, that's the green line, accounts for the great majority of water consumption in the U.S. The other sectors, domestic and public, the thermoelectric, freshwater sector, industrial and commercial, and finally livestock and aquaculture sectors use relatively little water compared with agriculture. Certainly there are exceptions to this depending on where specifically you are, but overall, agriculture is where most of the water goes. I need to make clear that water consumption is a small percentage of total water withdrawal. In most sectors, most of the water that is withdrawn returns to the stream and is then available for use by someone else. So we, in our modeling of water demand, are focusing only on water consumption. Here's a map showing the percent change in water consumption from the recent past to to 2080, or to a multi-year period centered at 2080, showing, perhaps surprisingly, decreases in water consumption over much of the West and increases in much of the East. A large reason for this is the projected irrigated area in the West and the East. Irrigated area in the West has been declining since about 1980, and we're assuming here that that decline will continue, which is the principal reason for the projected decrease in water consumption in the West. You see one big exception to that right here, this very deep red basin in the upper part of the lower Colorado River Basin. That's deep red, indicating a large percentage increase, largely because of Las Vegas. That basin is largely desert. Most of the use occurs in the Las Vegas area. There's little agriculture in that basin, so the most of the water consumption is in the urban sector, and it's projected to increase, and significantly. In a lot of the other western basins, agriculture is the predominant water user, and since irrigated area is decreasing, and also use per acre is decreasing as the ag sector in the West becomes more efficient. This results in a projected decrease in water consumption. In the East, as you can see in the graph on the bottom right, irrigated area has been growing, and we're projecting that trend to continue, which is a large part of the reason for the projected increases in consumption in the East. Here, what I've just been showing you is without the effect of climate change on water use. The two maps on the bottom here for the two RCP levels show those projected percent changes with climate change affecting the irrigation sector, the domestic and public sector, and the thermoelectric sector. These are our RCP averages across the 7 GCMs in each case. So step 4 is water allocation, where we take water yield, water demand, and enter those quantities into a water routing model. We use the WEEP model to simulate water allocation. And what's going on here is that the model keeps track of water storage, water availability, water yield, water flows from upstream basins, trans-basin diversion capacities and possibilities, the in-stream flow constraint, etc., and simulates what happens to water throughout the different connected networks of river basins. The water potentially available for delivery to off-stream uses in a basin in a given month, I should say, not year, equals water yield within the basin plus inflow from upstream basins plus net trans-basin diversion into the basin. This could be a negative number, plus water left in reservoirs in the basin or in upstream basins in the previous year after accounting for reservoir evaporation, minus the in-stream flow constraint, minus any required release from the basin to satisfy downstream demands. We used a simple set of priorities in our simulation of water allocation, where in-stream flow was given the highest priority. So if water was available in a given basin in a given month, that in-stream flow constraint was met. Secondly, off-stream demands were met in the basin or in other basins that were accessible from a given basin. And thirdly, if water was left over, it was stored to be available in future months and years. You see in the bottom left the storage capacities of the different basins. And in the bottom right, the basin interconnections. The blue lines are just natural flow paths from upstream to downstream, and the yellowish lines are the trans-basin diversion possibilities among basins. Because of all these connections, there is one very large network of interconnected basins that covers pretty much all of the West and much of the rest of the country, all the way over to here. Oh, sorry, all the way over to here and then back. So in total of the 204 basins, 145 of them are connected in a large network. And then there are smaller networks here in the Northeast, along the Atlantic, in the mid-Atlantic states, a couple of other basins in Texas that are small networks of connected basins. So step 5 is simply to compare water supply and demand and to keep track of when water demand exceeds water supply, and therefore there is a shortage. And this is simply the result of the water routing simulation. So here are some results for 4 25-year periods for each basin. It's giving the proportion of months within the 25-year period when shortages occurred. So if a basin is white, there was no shortage during the period in that basin. The second category there, 0.01, is a frequency of at least 3 months among the 25 years or across the 25 years. So essentially it's 1% of the months incurred a shortage. And so on through the scale there. So a darker color indicates a higher frequency of shortage. You see in the upper left, for the past period, quite a few basins with significant frequencies of shortage. I need to qualify that. Remember that we are at this point assuming only renewable water supplies. In other words, we're not allowing groundwater mining, when in fact, in many of these basins shown with significant shortages for the past period, in fact, a lot of groundwater mining occurred, which actually allowed many of those basins to avoid the shortages we are showing. We'll get to the groundwater mining issue later when we get to look at the effect of adaptations. You can see Moving to the near future, quite an increase. And this, I'm showing means across the 14 different futures here, so keep that in mind, and we'll get to some details in a moment for the different futures, but you can see quite an increase. Remember, the precipitation levels, by and large, were decreasing in the near future in these GCM projections. Some alleviation in the from the near future to the mid-future, largely as precipitation levels are increasing, and not much change between the mid-future and the far future. Again, it's a complex, but some increase. It's a complex mixture of changes in temperature, precipitation, and water demand over time that we're seeing the result of in these maps of shortage frequency. I'll just show you one result at the monthly time step. This shows the percent of the shortages occurring in the different months, and both in the east and the western halves of the country. The shortages are concentrated in the late summer, mid to late summer. So here are the maps of shortage frequency for 4 of the 14 futures. I'll show you the others in a moment, just quickly. But first of all, just taking a look at these two, you see the BCC model at the top, RCP 4.5 on the left and 8.5 on the right. And there's quite a difference with this GCM, the BCC model, quite a difference in shortage levels between the two RCPs. When you move down to the lower maps from the Canadian model, first of all, compared with the BCC model, shortages are much less. Secondly, there's not much of a difference between the two RCPs, the left and right maps at the bottom. Third thing to notice is that especially with the RCP 4.5 on the left, there's a big difference between the two models in the resulting projections of shortage frequency. So here are 2 other models. I'll go back to where we were and then forward again. See that the general areas of shortage are quite consistent across the different futures. I'll go to the next 4. They're quite consistent across these different futures. There's a lot of fine changes from one to the next, from one future to the next, but the basic locations of shortages are quite consistent. And here are the last 2 of the 14 futures. Another way to look at this is here. The top row, the top 2 maps show the RCP averages in each case across the 7 models. And then in the middle you see the minimum levels, and at the bottom the maximum levels across the 7 GCMs in each case. So quite a range between the minimums and the maximums, giving you a rough idea of the uncertainty about these future shortage levels. Okay, on to goal 2. We're almost done. What we do now is impose some change in some aspect of water demand or supply and rerun the water routing model for different futures, and then compare the resulting estimates of shortage frequency with those obtained without the change. Simple without framework. Well, now I'm going to show you results for these 6 different adaptation options, and although I should say there are 5 adaptation options in one change that's really not an option. It's just to see the effect of some different estimates of future irrigated area and irrigation application depth. That's the 3rd one down. The Economic Research Service folks used a much more sophisticated approach than we did to estimate future irrigated area and irrigation depth, how much water is applied in a given acre. So we incorporated those projections, which are quite different from ours in a lot of cases, a lot of places, to see how sensitive our results were to doing, I think, a much better job with the ag sector. So the other changes are from the top: larger reservoirs. We made all of the reservoirs 50% bigger. We increased the storage capacity by 50%. Certainly not a realistic option in most cases, but we're just trying to see what the effect would be. How successful could such a change be in reducing shortages? Our second one was to decrease irrigated area everywhere by 10%. The 4th one is to decrease thermal electric water consumption gradually over the rest of the century, reaching an 80% decrease by the end of the century. The 5th one is to lower the in-stream flow constraint from 10% of mean past flows to just 5%. And the last one is to allow groundwater mining. So to do that, we had to have some estimate of the amount of water that could be mined in a given year or month. I don't have time to go into how we arrived at those levels of possible groundwater mining, but they're based on past levels. And you see in the map in the bottom right the average annual past groundwater mining estimate as a % of total annual withdrawal. So here is the one result of looking at the effect of those 6, or I should say again 5 adaptations and 1 other change. That's the ERS levels of ag irrigated area and water application. So first of all, on the left, increasing reservoir size by 50% removes in each of the 4 25-year time periods about 5 basins from the shortage list. That might be surprising since we're increasing reservoir size by so much. And the most important reason why increasing reservoir size has such a modest effect on shortages is that the shortages were largely caused by lack of water. And so if you don't have water to keep the reservoir full in the first case, if the reservoir has essentially become empty, and therefore you have shortages, increasing the reservoir size is not going to be helpful. That doesn't mean that new reservoirs in locations that don't have them in specific situations couldn't be helpful, but large downstream reservoirs but increases in the storage capacity of large downstream reservoirs is not likely to be a generally effective adaptation. Secondly, reducing irrigated area by 10% had a modest effect as well. I haven't fully digested that result and understood it, but so I can't say much about it at this point. This is all quite preliminary, but it was modest. The ERS levels have a substantial effect, but quite modest as well. Notable though, they are projecting lower irrigated areas in the east than we were, and they're projecting lower water applications per acre in both the east and the west. And I think that's largely because of a bigger direct effect of increasing ambient CO2 levels on plant water use. Their model assumes a bigger impact of the CO2 increase on plant water use than we were. Fourth, adaptation or change there, the thermoelectric 80% decrease by the end of the century has a very modest impact. And that's because although a great deal of water is withdrawn for power plants, especially in the eastern part of the country, not that much is consumed, and so compared with other uses, and so at the scale we're modeling things at the HUC 4 level, the impact is modest. Again, in a certain specific location, it could have a big impact. Where in a basin, small basin, where a power plant is the major user of water, the impact could be significant. But at the scale we're modeling water use at, the impact is modest. Now for the last two, reducing the in-stream flow constraint and allowing groundwater mining. These are are shown here as to be the most successful approaches. The in-stream flow constraint reduction is certainly a worrisome option to anyone who cares about riparian condition, in-stream flow, water use, aquatic environments, etc. And what this is telling me is that as shortages become more of a problem in the future, as the climate changes and the population grows, there will be increasing pressure on existing in-stream flows. Finally, groundwater mining. It's the most successful approach. As I mentioned before, it's an approach that's been used for many years. Indeed, it's allowed water use levels to grow in many basins way beyond the capability of just renewable water supplies to maintain. And this is showing, I think, similar to the in-stream flow case, that there will be continuing pressure to continue to mine groundwater supplies, even though it's not a strategy that will work forever. many aquifers have limits that will be faced. In addition, it will become gradually more expensive to pump as groundwater tables drop. I think I'll just skip this summaries. We can cover some of this during questions if there's interest. Here's a list of publications from our earlier work, which will be included in a PowerPoint if it's made available. So thank you very much, and we'll see if there are any questions.
Okay, thanks, Tom. That was absolutely fascinating. We do have a couple questions that have come through. So the first one is, how would you expect increased water use efficiency in agriculture, for example, to compare with the adaptations that you have shown?
So I'm assuming in my projections, a continuation of improving water use efficiency in the ag sector. Let me go down here if you can still see this. So I didn't show this earlier, but this shows 4 major water use sectors, and in the bottom right is the withdrawal per acre in the east and west, and you can see in the west use is higher per acre than in the east. That's partly because flood irrigation has been much more common in the west than in the east, and because the climate is different in the west and tends to be drier. Anyway, use per acre in the west peaked in the 80s. 1980 is, in this case, given these data, which come from the USGS. They do a large assessment every 5 years of water use across the country. It's been dropping pretty consistently since then, and I'm assuming that it will continue to do so. And that's partly why you saw all that blue in the west in the map showing future overall water use. So the question was, what would the effect of even more improvement, even greater reductions per acre? And I don't have the answer. It's a good question. It's certainly something that we can address with our modeling, quite easily address. But I would expect that the effect of realistic improvements beyond what we're showing would not be great. But there's one other way to look at this, and that is that the ERS projections of future water use per acre were lower than ours. So if I were to show lines in this bottom right graph based on the Economic Research Service's projections, those lines would be lower. And as you saw in the bar graph near the end, the effect of assuming the ERS levels was not great. I guess that's all I can say at this point, but certainly it bears a closer look at in the future.
Great, thanks, Tom. We've got quite a few other questions coming through. So what is the resolution of the CMIP-5 data that you used for the study?
It was the same 1/8 degree resolution, roughly a 12-kilometer grid cell, as we used for the Vic model.
Okay, great. The next question is kind of a deep-seated one. So apparently there's no one-size-fits-all solution for the shortage for all basins. Do you have any ideas in terms of coming up with tailored solutions for specific basins within your models?
Not yet. I mean, the question is very good. Situations differ greatly across the country from one place to another because, first of all, as shown, precipitation is projected to go up in some places and down in others. Secondly, some areas are big ag areas where agriculture uses most of the water, and other areas are quite different. So the situations are very different. Some areas have pretty heavily developed their reservoir storage capacity, and maybe others have not done so as much, especially in the east. And so yes, the solutions will likely differ quite a bit from one location to the next. We haven't yet sort of separated areas of the country and seen what tends to work best in certain regions. The bar graph, for example, that I showed, here is a summary across all the basins. And so it doesn't tell you a lot. It just gives you a first look at the situation. If you created a separate graph for different parts of the country that are, for instance, areas that are receiving more precipitation versus less, or some other breakdown, you might get quite a different picture. And that's another thing that would be very useful to do as we go forward with this study.
Okay, so the next question has to do with your selection of the 14 GCM future scenarios and how you selected those particular ones among the over 230 other scenarios to choose from.
So when we were looking for climate data for running the Vic model, it was a few years ago now, there were 20-some different models to choose from where we were looking at the CMIP-5 based data. Each model had been run for various different RCPs, so there were quite a few different projections. But anyway, we were somewhat constrained by the wind speed data that was available to go along with the precipitation and temperature data. The Vic model required, as we were going to use it, wind speed, and we used essentially that constraint in deciding which models to use. We chose the ones for which we could also obtain wind speed data. I think I think it is the case that additional downscale data are currently available, and so if we were to do this again today, we would have more models to choose from.
Okay, well, that's the last question I'm seeing in the queue. So I'll just do a couple housekeeping things and keep an eye out, see if any more questions do come up. As I mentioned, the recording of this presentation will be available on our YouTube channel. We'll send out a direct link for the video as well as soon as it's available. Next week's webinar, scheduled for April 27th, again at 4 p.m. Eastern Time, will be presented by Dr. Liz Mack from Michigan State University, and she'll be discussing the socioeconomics of water. You're already registered for the entire series, so you don't actually need to do anything. There'll be an auto-generated email that provides the webinar link and call-in information that'll be sent out the Wednesday prior as well as 1 hour before the webinar. So unless anyone has any additional questions, I think we're ready to wrap up right on time here. Thank you so much, Tom. We really appreciate your time and hope everyone has a wonderful day.